sound. Yes, no.
Okay, sir. So thank you very much for giving me the opportunity to give lectures in this AFS2, and I'm very much happy to discuss with the students and interact with the students. So let me just say that if you have any doubts or any comment, please unmute yourself and ask questions, and you can stop me at any moment. So only thing that you can do that you can unmute yourself and ask, because if you write sometimes I may not be able to see the comments, so it's always better to ask questions. And so to, okay, so let me start by recalling the very first ring that we encounter in our, I think from school days, even without knowing the definition of ring, that is the set of integers. Yeah, so this is the usually we say it as a ring of integers. Yeah, and as we have seen several interesting, and in fact we know the several interesting properties of this ring of integers. For example, in view of algebra or in terms of algebra, what we know that every subgroup of, so if you try to see every subgroup of so this if you think of this Z as a group with respect to addition, so it is an abelian group, and we know that any subgroup of Z is of the form is of the form uh, m times Z. Yeah, where so here m is for some integer, m belongs to the set of integers. And what we know that if you, since we have studied the notion of ring, and we also can see that this mz is also an ideal. Yeah, mz is also an ideal. Yeah, an ideal. Yeah, in terms of ideal, and moreover it is a principal ideal. Yeah, and this notion of principal ideal, I think you have discussed in the previous lectures. And so what we know that so every ideal of, and in fact in terms of this ring theory and ideal, what we know that every ideal of Z is in fact principal. Z is principal. Yeah, so it is principal. And so that is because any ideal, if you try to see, that will be additive subgroup of Z, and any subgroup of Z will be of this form, and this is an ideal you can check. And so what is the advantage that we can gain out of these structures that the set of integer has, that one can define? So well, we know the definition of GCD from our high school days, but here we can define that GCD in terms of the notions coming out of these ideals. Yeah, so for example, if you take two, say, non-zero integers, so for a, b not equal to 0, if you take two integers, so how one can define the GCD? And the defining GCD in terms of ideals, we will see that we'll have advantage to generalize this notion of GCD for general rings, general arbitrary rings. So let us try to see, and I hope you have studied these things in previous lectures, so I'm just recalling. So what you can do, that look at the subgroup generated by A and B. So look at the subgroup, say, generated by A and B, and this, and subgroup generated by this elements A and B inside this ring of integers, are this group Z will be of the form AZ plus BZ. Yeah, so this will be a subgroup of Z, which I will write as a notation as Z. So this is notation is a subgroup. Yeah, and we know, as we have discussed, that any subgroup of this Z is an ideal. So this is an ideal, and since Z and any ideal of Z or any subgroup of Z will have the form, say, some integers, say for example D times Z. Yeah, so therefore what we can see that, so AZ plus BZ, this subgroup generated by this, will be generated by a single element. Here for some D belongs to Z. Yeah, And as it can be shown, or you can try by yourself to see that this D is actually D so this D satisfies the properties of GCD, satisfies the properties of GCD of A and B. Yeah, so this, that you can check, that means D divides A and B. And I hope that this divisibility also you have been discussed in previous lecture, that this divisibility can be understood in terms of containment. And this again, the second property, that if there is another number which divides A and B, then that number will divide this integer D. Yeah, so this, that you can prove by these properties here and the properties of the ring of integers. Yeah. So in particular, so if we take two integers which does not have any factor in common. So for example, if you take two integers A and B, and suppose they don't share any common factor other than the units like plus and minus 1, which are the units inside Z, then by this definition, what we can see, that by this definition of defining GCD, what we can see that this so ideal generated by AZ plus BZ will be equal to the whole ring Z itself. Yeah. And so what we can see that, so here one is here inside Z, so one can be written as so RA plus SB. Yeah, for some integers R and S inside the set of integers. Yeah. And so this is the property that can be used to prove an important result or proposition inside the set of integers, which is about these prime numbers. And so I will just write it as a proposition. I hope you know the proof that, so if you take, let P be a prime integer, so let P be a prime integer. Yeah. And AB belongs to the set of integers or ring of integers, then if P divides AB implies either P divides A or P divides B. Yeah. So this is very straightforward from this here that identity that we have written, because, and that I think, so can you give the proof of this thing? If you can give, then I will skip, and otherwise let me just, so can anyone unmute and say how we can use this one to prove this proposition? So if you can give some hints or idea, how can we proceed? So anyone can unmute and so am I audible or clear enough? You can say also, you can stop me by now. So let me just give a quick proof that, so what our aim is to prove that this either P divides A or P divides B. Yeah. So let us assume that, suppose this P does not divide A. Yeah. Then what we need to prove that P has to divide this integer B. Yeah. So P doesn't share any common factor with A. So P is not in this factor of A. So therefore they are co-prime, right? So they have GCD1. And this is just because P is a prime. And then if we use this identity, this one, so what we can write, that we can write as RP plus SA is equal to 1. Yeah. And what we can, so here for some R and S, for some integers R, S. Yeah. And now what we need to show that P divides B. So what we can do, just we multiply by B throughout this equation. So what we can get from here, that RPB plus SAB is equal to B. Yeah. Now what we have given the hypothesis is that since P divides AB, so therefore if we use this fact, what we can see that, so P divides AB and P of course divides this one. Yeah. So therefore what we see that, so P divides this AB and P divides this factor. So therefore P divides this whole thing. So therefore P divides RPB plus SAB. And this, if you try to see, that is exactly equal to B. Yeah. So therefore this is this identity is able to give that the very important property that a prime integer satisfies. And this also can be described in terms of containment, and that we will see later, that how this divisibility can be interpreted in terms of containment of two sets. Yeah. Or in terms of the ideal generated by these elements will be contained in one or other. Yeah. But so let me just point out that we are recalling here the properties of the set of integers, and our aim is to somehow generalize or extend these notions for general ring, at least for the rings, nice rings, for example integral domains, where we have at least flexibility of the cancellation of elements. Yeah. So at least for those rings we should be able to extend, and the question is how to extend those properties. Yeah. So this is the aim of our lecture. So but let me recall certain things that we are going to generalize or extend, and that is very much clear from this very well ring that we know from our childhood. Yeah. So this is the one thing, and another important property that this ring of integers has is known as this fundamental theorem of arithmetic. So let me just write down, this is the fundamental theorem of arithmetic. Yeah. So this what does this essentially says, that this prime numbers that we have discussed are prime integers that we just discussed actually are what does this theorem says actually are the building blocks for this set of a ring of integers. Yeah. And so let me just write down that every, so if you take any non-zero integer, yeah, so can be written as a product. So A can be written as say some constant C times P1, P2, and for example Pk, where C is either +1 or -1. And as you can see that this +1 and -1 are the units inside this ring of integers. And PI's here, PI's are positive primes. Yeah. So are positive primes, and here K is bigger than or equal to 0. Yeah, K is non-negative. So please note that here in this way of writing, so here PI's are positive primes, but it may happen that means, for example, P1 may be equal to say P2. That means I am not telling that these PI's are distinct. What I am telling, they are just positive primes. So they so some primes may be equal to each others. Yeah. So that we have written by this include by including multiplicities as well. Yeah, in this way. Okay, so can so just I would like to give a quick proof of this fact again, and then we will proceed further. And can anyone so do you know the proof of this fact, fundamental theorem of arithmetic? It is very simple and based on an induction argument that you know, and I think I can skip this for maybe tutorial, and you can try there also. Yeah. So is it okay if I give it as a tutorial problem, so our
Yes,
homework? Yeah.
yes, it is fine.
Yes, sir.
Yeah. So this is homework. Yeah. And so we have this very nice important structure that this ring of integers has, that these primes are actually the building blocks for this ring of integers. And so now so let me just also recall another similar ring which we know and in the previous lectures have been discussed a lot, is about this polynomial ring. So this is about this polynomial ring. And so here that is fx, yeah, and where f is a field, f is a field. And what I would like to say that the ring of the structures inside the set of integers has similar structures that these polynomial rings also have. Just one has to make a dictionary from this set of integers to this polynomial ring with this ambient integral domain should be a field. And so one can make, for example, that this ring of integers, so z here we have, for example, very nice. So for example, it has that absolute value here, and on fx this absolute value that we will again come in the coming lectures. So here this dictionary can be understood for fx in terms of the degree of polynomials, degree of px polynomial, say fx. So let me just write down as fx. Yeah, and also whatever I have just discussed here, that GCD and this fundamental theorem of arithmetic results, those also can be just written down for this polynomial rings. And so let me just also recall those things once again, and I will just quote it as a theorem. So here f is a field that we know, that we have by the very beginning, and we have fx is the polynomial ring in one variable. So that is this polynomial ring in one variable. So in one variable over this field f. And then what the properties that it has, that that you can similarly prove the way it has been proven for this ring of integers here, that if you have two polynomial which doesn't share any common factors, then so let me write down that if f and g belongs to your polynomial ring fx, and such that they are co-prime, they does not common factors, then you can prove that there exist these two other polynomials, say r and s, belongs to this polynomial ring f of x, such that so let me just write down a bit. I think this word here, bit this rf plus s times z is equal to 1. Yeah, so this again you can prove the very much similar the way we have just discussed. And I think here it has been proven that if f is a field, then fx is a principal ideal domain. If not, we will come at some point, or it can be discussed in the tutorial when we discuss the notion of principal ideal domain. And so it is again, once f is a field, then it can be proven that this polynomial ring fx is a principal ideal domain. And so that one can mimic the arguments from the set of integers to this polynomial ring. Yeah. So the second one that we have proven for prime integers here, what will be the analog of here prime integers? One need to define the notion of so-called irreducibility of a polynomial or irreducible polynomial. And we say that here, just let me, I think that also you have been discussed in previous lecture. So let me just still recall that what we mean by an irreducible polynomial. So we say, for example, a polynomial, say p of x, inside this polynomial ring is called irreducible. So we say that it is irreducible if, first of all, it should not be the constant. So if it is not constant, if it is if so, let me write if it is not constant, and also the only divisors of this. So what I would like to say that, and if it's only divisors of lower degree lower degree are constant itself. So what does it says that, so if you have polynomial and we say that the polynomial is irreducible, so first of all we should not take just the non-zero elements of the field. So here we are not taking the constants are here non-zero elements of this field F, so they are known as constants. So that should be a non-constant element. And if you are trying to write this polynomial into a fact into two other polynomials of lower degree, then those lower degree polynomials that should occur are as only constant polynomials. Yeah, so you cannot, what does it say, that you cannot break this polynomial into non-trivial lower degree polynomials. Yeah, so this is the notion of irreducibility. And here, so the second property of these primes that we have proven that this, if a prime integer divides product of two elements, then that prime should divide one of the factor. Yeah, so here also one can write down that if an irreducible polynomial, so irreducible, say polynomial, say px inside this polynomial ring fx. So if so happens that px divides z, this implies that either px, so either px divides f of x or px divides g of x. And this again you can prove again by using the similar arguments that we have given for the ring of integers. And the third one again is about this, like the fundamental theorem of arithmetic. Here also one can write that if you take a non-zero polynomial f of x, here say is non-zero polynomial inside this polynomial ring, then f of x can be written as some constant c times p1, p2, and so on pk. And here pi's are here c. So let me just say that here c is a non-zero element inside this field f, and pi's are monic irreducible polynomial in fx. Yeah, so this is the thing, that an analogy that one can make from this set of integers to this polynomial rings. So let me just stop and ask, so do you have any doubts or comments or any question? If you have, so please let me know, and then we will proceed further. Okay, fine. So if there are no doubts, so let me just now comment here about this constants c that we can see inside this factorization of this polynomial are in this fundamental theorem of arithmetic that we have discussed here. Yeah, and here this c, as we can see that c is either +1 or -1, which is a unit or invertible elements inside the set of integers. And here this c are the invertible elements inside this polynomial ring, which is fx, are this non-zero elements of the field f itself. Yeah, so they are the what is so-called the units, and one can match this analogy in this way. And the one thing that I would like to just say that this one can, so this if we take this unit c, actually makes so if we write c separately as +1 or -1, which will be able to allow us to restrict these primes as a positive primes here. Yeah, And if you allow C, means if you ignore the occurrence of C, then you can see that these primes may be positive or negative in their factorizations. Yeah. But if you separate out this constant C, then it will fix the primes P as a positive primes. Yeah. And similarly here also the analogy of positiveness translates into the monicness here. Because so if you allow this constant C to be separated from other factors, then you can make each fact is irreducible polynomial to be monic. Yeah. So this is the advantage that one can have, and in this way, if you separate it out these constants, the statement about uniqueness of this factorization is somewhat much simpler, and so one can handle it properly. Yeah. So this is the advantage that this constant taking out from the other factors makes possible. Yeah. So this is just I would like to mention, and so let us try to see some baby examples or simple examples that we know, and so then we will proceed further. And so the example that we would like to discuss here, of course, the very I think inside these things we have studied very much about this field of complex numbers. Yeah. So if we try to look at this polynomial ring Cx, where C is a field and C is, so this is the field of complex numbers. Yeah. And if you take any polynomial, for example, so f of x, non-zero polynomial, which is inside this polynomial ring C of x, then we can we know a very well nice factorization of this polynomial. So what we know that this property of this field of complex number, that if you take any polynomial with coefficient from the set of complex numbers, then it must have a root inside this C itself, inside this field of complex numbers. And if you use that property, then what you can see that the irreducible polynomials inside this Cx are precisely the linear polynomials. Yeah. And so if you take any non-zero polynomial, so this non-zero polynomial inside Cx can be written as a product of this irreducible linear polynomial. So this will be like C times x minus alpha 1 and x minus alpha 2 and so on, x minus alpha n. And here n is somehow telling that this polynomial, this factorization is linear, and this polynomial that we should start is of degree n. So fx and this, and degree of fx, for example, is n. Then you have n linear factors, and where c is any complex numbers, and here alpha is are the roots, and these roots may be repeated, but it is written in terms of linear terms. Yeah. And also one can see, so let me, I think I have not uh, told that this factorization is unique. So let me also mention here that this factorization is unique here up to the ordering of terms. Yeah. So here, and the similar thing for this fundamental theorem of arithmetic, I think I have not written down, but I think I have told. So this factorization is unique up to the ordering of the terms, ordering of PIs, yeah, these primes. And so here uniqueness of this factorization over Cx can be proven, and that you can try by yourself. And so this is the first simple example that we know. And the second example that we can take is over R. So if we take this polynomial ring Rx, yeah, and if we take any polynomial, and down the factorization of this polynomial into irreducible factors, then how one can write it down. Yeah, so let us start with any non-zero polynomial fx inside this uh, polynomial ring over Rx, polynomial ring over R, and here R is also field. Yeah, R is field of real numbers. Of course, here usual addition and multiplication of real numbers. And yeah, so here I am not telling these operations, and once if I am not telling the operations, that means the usual operations that the set of complex numbers or set of real numbers has. Yeah, so field of real numbers. And so if you take any non-zero polynomial or with real coefficients, so we can always think this polynomial inside the set of complex numbers. That's true. Yeah, because Rx sits inside this polynomial ring Cx, and there inside Cx we can factor this fx as a linear factors. Yeah, so what you can write that fx as some constant times x minus alpha 1, again x minus alpha 2, and so on, so forth, x minus alpha. Yeah, and of course here I am assuming that the degree of this polynomial fx is said n. Yeah, so this is a factorization of this polynomial with real coefficients inside the this polynomial ring Cx. Yeah, but what our aim is to factor this polynomial fx into irreducible factors, where the irreducible factors should be a polynomial inside Rx. Yeah, so this is our aim, and how to do that. Yeah, so what we can do that, first thing we should so therefore what our aim is to classify the irreducible, classify the type of irreducible polynomials in Rx. Yeah, that means what are the irreducible polynomials inside Rx? Well, the linear polynomials are always irreducible over any polynomial ring over a field that you can see. Now what happens if you take degree more than 2? So if it is, for example, degree 3, then also we know that a degree 3 polynomial with real coefficient has one real root. So therefore it will again factors into a degree 1 and degree 2 polynomial. And similarly, odd degree also can be reduced to the discussion of an even degree polynomial with real coefficients. Yeah. So therefore here is the problem, that if you take a polynomial with real coefficients, say for example even degree, and the very simplest even degree polynomial is the degree 2 polynomial. Yeah, and so for example if you take degree 2 polynomial with coefficients from Rx, yeah, so what we can say whether it is irreducible or not. And for degree 2 or 3 degree 2 or 3 polynomial over any field, you have very nice result that says that in order to check the irreducibility, enough to check the roots of that polynomial. Yeah, and for degree 2, if it has a real root, then it can factor into linear factors with real coefficients. And of course if it does not have a real root, that means that degree 2 polynomial is irreducible. Yeah, so now for example, so the quadratic polynomial, so let me just write down the quadratic polynomial. Say qx, say for example gx belongs to Rx. Yeah, yeah, so what it has, that what we can know, that if alpha is a root of that polynomial, uh, so in fact this is true for any polynomial with real coefficients. So let me write down here that if alpha is a root of fx, then alpha bar is also a root of, then alpha bar is also a root of fx. Yeah, that we can see just because if we just write down this as f of say alpha bar, and by the very definition of this polynomial, so for example, if the polynomial fx is of this form, say for example, this fx can be written on the one hand as a0 plus a1x plus and so on plus a and x to the power n, then what we see from here that we can write f of alpha bar as a0 plus a1 alpha bar plus and so on and so forth an alpha bar to the power n. Yeah. And since these ai's are here, ai's belongs to the set of real numbers, so what we can see from here that this can be written as a0 bar plus a1 bar alpha bar plus and so on and so forth an bar alpha bar to the power n. Yeah. And so this is exactly equal to, if you try to see that, f of alpha whole bar. Yeah. And so therefore what we see that if alpha is a root of fx, this implies that alpha bar is also a root of this polynomial. Yeah. And so this is equal to, so 0 bar, which is equal to 0. Yeah. So therefore what we see that if alpha is a root, then alpha bar is also a root. Yeah. And now let us try to come to this quadratic polynomial gx. So what we see from gx that gx can be then factors. For example, if you have irreducible quadratic polynomial, then gx is x minus, can be written as x minus alpha and x minus alpha bar. Of course, here I am taking, for example, the monic quadratic polynomial. Yeah, so here let us try to take monic so that the leading coefficient will be 1. And if you try to see, so this will be x square minus alpha plus alpha bar times x plus alpha alpha bar. Yeah. And as you can see that this alpha is a complex number, then alpha plus alpha bar is a real number. Yeah, this belongs to R. And again, alpha alpha bar will also be a real number. So therefore what we see that if you take for example for example degree quadratic polynomial with real coefficients, yeah, and suppose it has a pure complex roots alpha and alpha bar, and then if you multiply it out, so this multiplication will give a quadratic polynomial with real coefficients. So this belongs to RA. Yeah. So therefore if we club if for example in this factorization of thinking this factorization inside, so inside C of x, if we club the conjugate roots all together and if we multiply them out, so they will be degree 2 polynomial with real coefficients. Well, and if there is a real root, then of course that linear polynomial will correspond to a polynomial inside Rx. So therefore what we see that from this discussion that any, so let me just write down that any fx belongs to Rx can, so of course this is non-zero polynomial, can be written as a product of irreducible polynomials of degree 1 and 2. Yeah. So therefore what I would like to say from this statement that if you take any polynomial with real coefficients and if you write that polynomial in terms of irreducible polynomials, so the irreducible factors occurring in this factorization of fx will be either degree 1 or degree 2, and that we have just discussed here. So by the way, so far any questions or comments? Okay, fine. Okay, so now let me proceed further. And so now what we are going to now let me ask a very simple question, and again we will be discussing a very nice property that this polynomial ring have, and the nice property that we would like to discuss. So let me ask a question and for you that if you take this, for example, z mod 8z, yeah, and if you look a polynomial inside this polynomial ring Z mod 8 ZX. Now, for example, if I take the polynomial as x square minus 1. So can anyone of you tell me that what are the factors of this polynomial, or what are the roots of this polynomial with over Z mod 8Z? Yeah. So if you try to see that, well, we know, for example, over the if we write a polynomial over the field of complex numbers, then we know that this polynomial has exactly n roots, exactly degree many roots inside this set of complex numbers or the field of complex numbers. But if you change your this ambient ring as which is not a field, for example, even this is not an integral domain. So what we can say about the roots of this polynomial? So can anyone say that what are the roots of
1, 3, 5,
right?
7.
Yes, yeah.
7
So
also.
7 also, yeah. 7 because 7 corresponds to -1 inside Z mod 8Z. So well, we can write as x plus 1 as x minus 1. This is the one factor. And the other thing that you can write as x plus 3, well, and x minus 3. So the point of asking this question and writing this polynomial in two ways is to just point out that if in this discussion, if f is a not field, for example here, then writing this polynomial as a product of irreducible polynomials will not be unique. So that you can see from here that here we are writing this polynomial in two ways. And these writing two ways are completely different than the other because the elements 1, 3, 5, 7 are different inside Z mod 8Z. Yeah. So therefore, this writing factorization of a polynomial into irreducible factors will be unique inside the if you take as an ambient ring as a field. But if it is not a field, then you can see that the uniqueness is lost here. Yeah. And also one thing you can notice that as we see that inside the field of complex numbers, if you take a polynomial over C, or then it has exactly degree many roots. But here it is of degree 2 polynomial and it has 4 roots, more than the degree many roots. Yeah. So the thing that I would like to today prove is that if you take a polynomial ring over a field, then this polynomial can have at most degree many roots inside the field F itself. Yeah, and this is the theorem. And just I would like to ask, does this theorem have been proven in previous lectures or no? So let me just write down and then you can answer. So the theorem is that, so if you take if fx belongs to f of x and say fx not equal to 0 of degree n, then f has at most n roots inside this field f. And of course here f is a field, so let me just write down here f notation, I mean is the field. So does this theorem is proven, or you know this result, so that I can continue further. So
We mentioned actually, Sir also mentioned it.
okay.
Used also, yeah.
Okay,
Even
so
it is mentioned for integral domains also.
okay. So the proof
Not done.
not done. And so for integral domain, I think this result is true. Well, let me ask to the students. So do you know that? So instead, for example, here Z mod 8Z is not an integral domain, and we have shown that it has more than say degree many roots. And what about then the, yeah, of course, the natural question is then what can one can say about the integral domain. Yeah. So what about integral domains? And then the question comes for fields. Yeah. So
It's
do
true in case of it is true in case of integral domain.
means that means you are telling that if I take a polynomial over an integral domain, then this polynomial can have at most
n roots.
degree many roots inside that integral domain.
Yes.
Yeah, but unfortunately means for me the answer is still no. That if you know this real quaternions, for example, are of this IJK, and if you know this ring, then it's fine. Otherwise, so this is a real quaternions, and one can prove that this is an integral domain. In fact, it is a division ring.
But actually, we are assuming that integral domain is commutative here.
Okay, okay, so yeah, then it's fine. Yeah, if the integral, yeah, by default, okay, in the previous, okay, so let me, yeah, then it's
But
fine.
it is good anyhow. The mention
Okay.
you what you mentioned.
Yeah, so yeah, for me also, I did not mention so far, but for me also, when I say integral domain, good, thank you, Professor Satya, to point out. Yeah, I was forgetting that fact. For me also, as this Artin assumes that for integral domains, for him is always commutative ring with unity plus this definition of integral domain, which means it has no zero divisors. Yeah, but of course, yeah, so what I would like to just point out here, that even if you take a nice ring which is very much close to a field, there also this property may fail. Yeah, of course, here now this division ring is not commutative, but here also you can see that x square plus 1, this polynomial has 3 zeros in this one, more than the degree many roots. Yeah, but good that here, yeah, for me also, let me just write down whenever I say integral domain, and of course in this whole course of lectures I will be so let me just point out somewhere, let me point out here itself, that for me also integral domain is always this commutative ring with identity or with 1 plus has no zero divisor, has no zero divisor. Yeah, so let us try to see the proof of this theorem, and then we will proceed further. Yeah, and so the for the proof, so again this is again the proof is by induction argument. And well, so let me just, so this proof is by induction argument. And of course, in order to start the induction argument, one need to check at the very initial step. So an induction argument is applied. So induction argument on the degree of a polynomial. Yeah. So therefore, in order to start this induction argument, we need to check whether the result is true for degree 1 polynomial. So for n is equal to 1, so the degree 1 polynomial will be of the type, say, alpha x plus beta. Yeah, and here so this lies inside this polynomial ring over a field f. And well, so this has a, so the zero of this linear polynomial can be determined, and this will be exactly equal to, say, minus beta over alpha. Of course, here if we say degree 1 polynomial, that means alpha is not equal to 0. And so therefore you can write down its 0 as x is equal to minus beta over alpha. And since alpha and beta are the elements from a field, therefore minus beta over alpha is also an element of the field f. Yeah, and so this is the only root of this polynomial, which and this root lies inside f. Yeah, so therefore for n is equal to 1, we are done. Yeah, now again by the induction argument, we need to assume this argument for the all polynomials of degree less than degree of f. So assume the result is true for polynomials, for all polynomials, for all polynomials of degree less than or equal to n minus 1, and then we need to prove for degree n. Yeah, well, now aim is to prove the result for degree of f is equal to n. Yeah, and now so if there does not exist any root of this polynomial f inside this field f, then we are done, because in this case it has at most n roots, because no roots will imply that it has at most n roots. So let me just write that if there does not exist any root of f in f, then we are done. Yeah, then in that case it has no zeros or no roots inside f, implies that it has at most n roots in f. Yeah, now if so then we are done. If there exists a root, of f in f, then I think in the previous lecture we have been discussed the result that alpha belongs to the field f is a root of the polynomial f of x if and only if this linear factor x minus alpha divide this polynomial f of x. Yeah, so this result I think have been proven, and so we will use this result and the induction, and this is the key idea to prove this result, that somehow we need to use our assumption that we have assumed for degree less than or equal to n minus 1, and we need to break our polynomial into polynomials of degree less than n, and that is possible just thanks to this theorem which have been proven in the previous lecture, and which allows us to write f of x as x minus alpha times say g of x. Here g of x or g of x say belongs to f of x, and you can see that degree of g of x is equal to n minus 1. Yeah, and degree of g of x is equal to n minus 1. Yeah, now what we can say that if there exists, if beta not equal to alpha is another root of f, is another root of this polynomial f, then what we can see that f of beta will be equal to 0, and this f of beta is exactly beta minus alpha times z of beta. Yeah, and since beta not equal to alpha, so this is non-zero, so this is not equal to 0. Yeah, and we are inside a field f. Yeah, we are inside the field f, which is an integral domain, and it has no zero divisor, so this implies that z of beta has to be equal to 0. Yeah, so therefore what we see from this discussion that apart from alpha, if there do exist another zero of this polynomial f, will be actually a zero of a lower degree polynomial. Yeah, yeah, so therefore now what we are going to use, and therefore it's enough to discuss the induction arguments that we have assumed for lower degree polynomial. And so therefore what we can see that thus by the induction argument, that gx has at most n minus 1 roots inside f, inside this field f, and as you can see that this polynomial f and z differ by only a linear factor here, differ by only this linear factor, and so all this n minus 1, at most n minus 1 roots of g, which is also be a root of f, will lie inside f, and one root will actually give me at most n roots, and so therefore, and hence what we can see, and hence fx has at most n roots in f, n roots inside this field f. Yeah, so this is the argument for this proof of this theorem. And so do you have any questions or comments so far in this thing? If you have, please let me know, and then we will proceed further.
No, sir.
Okay, fine. So let me just now define certain notions that so far we have been using for polynomial rings, or this ring of integers. And so let me just define this thing for general integral domains. And here we are assuming integral domains so that we will have at least some nice property like this cancellation law should hold inside the ring. So we are assuming that the ring should be an integral domain, and by the very definition, for us integral domain means commutative ring with identity which has no zero divisors. Yeah. So let me just formally define this divisibility and all, and then we will. So here R for us is an integral domain. And then we are going to just define. So the first, so of course we will take the elements from A, B belongs to R, and we say that A divides B, that if there exists some element Q inside R such that this B is equal to A times Q. So this is the meaning of divisibility inside general integral domain. And we also say that A is a proper divisor of B. So A is a proper divisor of B if B can be written as, say, A times Q, where this neither A nor Q is a unit. So where this neither A nor Q is a unit. Yeah. So this is the meaning of proper divisor, because you can always, if you know some units inside the integral domain, then so proper divisor, I mean, for example, here you can always write any element. For example, here we are A, one can always write as 1 times A. Yeah. And 1 is, we have been assumed that it is inside the integral domain identity element, and so 1 is the unit in this case. And in general, so it may any integral domain may contain plenty of units. So what this proper divisibility, I mean that we are avoiding this writing this element as trivially. You can write trivially as like this, and if you have plenty of units, then you can write many ways. And so proper divisibility, I mean here that we are avoiding those kind of expressions in this way. That means A and Q, they should not be a unit. Neither A nor Q should be a unit. Yeah. And then, so again, we will say that, so if you take a non-zero, suppose A is a non-zero element inside integral domain R, and we say that A is irreducible. A is irreducible if first of all it should not be a unit. If it is not a unit, yeah, and if it has no proper divisors, and if it has no proper divisors. So the irreducibility of a non-zero element, we say that it is irreducible. So first of all, it should not be a unit, and it should not have any proper divisors. Then we say that the element is irreducible. Yeah. And another definition, so let me just write down. So far I have given, so here first this is the definition, and this is the second, and here it is the third one. Yes, third I should write here because I have taken this condition into account. So here this is the third one, and the fourth one is about associates. Yeah, so we say that the two elements, so A and A dash, are called associates. So of course this belongs to R, and this also be an element of R, are associates if A divides A dash and A dash divides A. So these are just the definitions that I have given. So you can try the examples maybe in tutorials to check what are the meanings of this for general integral domains. And I think now I am running over with the time, is it? So I would like to stop. So we will meet in the next lecture, and we will continue discussing this factorization inside a general integral domain. So okay, so Professor Satya, so